The best way to complete this chart is to first find the osmolarity, and then secondly find the tonicity of the solution, and then lastly the direction of water movement. So in our first example, we have 280 milliosmoles of glucose. Since it's already in the correct units, we don't have to do anything to it. And so to find the osmolarity, we just simply compare 280 with 280. Now since they're both equal, the osmolarity will be isoosmotic. As for the tonicity of the solution, we look to see in our solution if we have any urea. If we don't have any urea, we just simply take the same numbers as before. So we have 280 here, 280 there. Since they're equal, it will be isotonic. Now, to figure out the direction of water movement, all we need to do is look at our tonicity. Since our tonicity is isotonic, there will be no net change in water movement. If this was hypotonic, the direction of water movement will head inside of the cell. If it was hypertonic, the direction of water movement will head outside of the cell. So in our next example, we have 350 millimoles of urea. Now, since this is not in the correct units, we take 350 millimoles and we multiply that by one dissociable particle, since urea has only one. So 350 times 1, that will be 350. But this time it will be in the correct units of 350 milliosmoles. So now we compare that with 280. Now since we have more outside of the cell than inside of the cell, this will be hyperosmotic. Now to find the tonicity of the solution, since we do have urea, what we do next is we take 350 and we divide this by 2. So 350 divided by 2, that's 175. And we add that other half. So 350 divided by 2 is 175. And we add the other half of urea to the red blood cell. So these two are our new concentrations. So since we have more inside of the cell than outside of the cell, the tonicity will be hypotonic, and the direction of water movement will head into the cell. For next example, we have 280 milliosmoles of urea and 280 here. Okay. Now to find the osmolarity, since they're both already in the correct units, we simply just take 280 and 280, so that will be isoosmotic. As for the tonicity of the solution, since we do have urea, we take urea and we divide it by 2. So 280 divided by 2 is 140. And we add the other half to the red blood cell, which is 420. So now these are two new concentrations. Now since we have more inside of the cell than outside of the cell, the tonicity will be hypotonic, and the direction of water movement will go into the cell. And so our next example, we have 140 millimoles of CaCO2. Now since this is not in the correct units, all we need to do is take 140 and times it by the number of dissociable particles, which is 3, which is 420. And we compare that to the red blood cell. Now since we have more outside of the cell than inside of the cell, it will be hyperosmotic. And the tonicity, since we do not have urea, we can just simply use the same numbers as before. So that will be hypertonic. And the direction of water movement will head outside of the cell. Next example, we have 70 milliosmoles of urea along with 70 milliosmoles of glucose. Now since they're already in the correct units, all we need to do is add them together. So 70 plus 70, that's 140 milliosmoles. and we compare that with 280. Now, since we have more inside of the cell than outside of the cell, that will be hypoosmotic. Now, to find the tonicity, we just do the same thing as we did before. Since we do have urea, we take half of urea, which is 35. So we take away 35 from the solution, and we add 35 to the red blood cell, which is 315. So since we have more inside of the cell than outside of the cell, this will be hypotonic, and the direction of water movement will head into the cell. So our next example, we have 140 milliosmoles of urea and 140 milliosmoles of glucose. Now, since they're already in the correct units, all we need to do is add them together like before. So that will be 280. And we compare that with the red blood cell, which is also 280. Now, since they're both equal, the osmolarity will be isoosmotic. Now, for the tonicity, since we do in fact have urea, we take half of 140, which is 70. So we're taking away 70 here, making this 210. And we add 70 to the red blood cell, making 350. Now, since we have more inside of the cell than outside of the cell, this will be hypotonic, and the direction of water movement will head into the cell. So our next example, we have 140 milliosmoles of NaCl and 140 milliosmoles of glucose. Since it's already in the correct units, we just add them together, making 280. And we compare that with 280 of the red blood cell. Since they're both equal, it will be isoosmotic. Now, for the tonicity, since we don't have urea, we can just compare the numbers. So they're equal, so it's isotonic, and there will be no net change in water movement. Next example, we have 420 millimoles of NaCl and 70 millimoles of urea. Now, since this is not in the correct units, we just take 420 and we times that by 2. Since NaCl has 2 dissociable particles, urea has 1. So we just times them. 420 times 2, that's 0, 4, 8, and 70. And we add them together at the end, making 910 milliosmoles. And we compare that to 280 of the red blood cell. So since we have more outside than inside, this will be hyperosmotic. And since we do in fact have urea, so we have 70 milliosmoles of urea. So we divide that by 2, which is 35. We take away 35 here, making 875. And we add that 35 here, making 315. And since we have more outside the cell than inside of the cell, the direction of water movement will go outside of the cell and it will be hypertonic. For our last example, we have 280 milliosmoles of urea and 280 milliosmoles of glucose. Since it's already in the correct units, we just simply add them together. So 560. And we compare that with 280. Since there is more outside than inside, this will be hyperosmotic. Now, since we do have urea, we take half of 280, which is 140. So we minus 140 here, and we add 140 to the red blood cell, which is 420. And now, since they're both equal, the tonicity will be isotonic, and there will be no net change in water movement.